Hi, chemistry students. This is your Unit 11 lesson on the ideal gas law and Dalton's law, sometimes called Dalton's law of partial pressures. So first of all, I want to let you know that all the gas laws we have learned so far are based on the behavior of something called ideal gases. And an ideal gas is assumed to have particles who exhibit no attractive or repulsive forces and whose particle size is not significant, is insignificant. Whereas a real gas has intermolecular forces, particle volume, and can change states. And what this means practically is that the gas laws work really well within a certain parameter of temperatures and pressures. And those would be temperature and pressures for gases where they are not close to where they're going to condense into liquids. That is when there are really no intermolecular forces acting on them. So they are really useful. High temperature and low pressures are conditions where there are usually not too many intermolecular forces at play. So at high temperatures and low pressures, they are effective because the intermolecular forces at those conditions are least effective. Now, high temperature and low pressure is relative to the gas, and there are a lot of gases where normal conditions, like room temperature and atmospheric pressure, are considered high temperatures and low pressures for those gases because they are very far from being at conditions where they would condense. And so ideal gas laws are really good at predicting things for many, many gases, the ones that are pretty much familiar to us, like helium or hydrogen or oxygen or carbon dioxide or neon or krypton or fluorine or chlorine or xenon. You can see there are a lot of gases where the ideal gas laws are very predictive because they're nowhere near the temperature and pressures where they will start to condense. And so that's why they're useful. So when do gas laws work? At high temperatures and low pressures where intermolecular forces are least effective for those particular compounds. Now, if we get down to, though, for these particular gases, to like really, really high pressures, like several hundred atmospheres, or very, very low temperatures, like getting down towards absolute zero, then no, these gas laws will not be predictive. But under conditions most people work, they will be. So we have something called the ideal gas law, and a way to remember it is this word, this nonsense word, Pivnert. Now what it says is, and you've seen in the previous gas laws, that certain relationships give you a constant. That's why you can predict how things change. Well, somebody somewhere looked at the four variables that affect gases: pressure, volume, N being moles, and T being temperature in Kelvin. And they set up this ratio, and every time they set up this ratio, no matter what they did with the variables, they got the same number, a constant. And R is called the gas law constant. It's a constant that will depend on the units chosen, but it will always be given to you. So in other words, you're always going to get this constant number based on the units that are plugged in here for you. Now, it's normally written as PV equals nRT, and hence the nonsense word Pivnert. Again, let me show you what I mean by what this gas law constant looks like. So here are all the different values of R, and you will not have to memorize any of them. You will be given, particularly the ones in red, because they're the most common. Now, what's the difference? So you'll notice that it is PV over NT gives you R. Now, you'll notice these right here, these are not formulas. These are the units of the gas law constant. Notice pressure would be measured in atmospheres, volume in liters, N would be moles, and T would be the temperature in Kelvin. So when pressure, volume, moles, and temperature are measured in these units, this ratio is always going to give us the number 0.0821, always. Now, what if we don't measure pressure in atmospheres? Well, then we're going to get a different kind of a number. So let's look at this one, for example. If we measure pressure in kilopascals rather than atmospheres, but keep liters, Kelvin, and moles the same, you can see that the number changes to 8.314. Now, the number changes, but the value doesn't. If you recall, 1 atmosphere equals 101.3 kilopascals. So think about it. If I multiply this number by 101.33, I pretty much get this number, 8.314. So all we're doing here is changing the unit of pressure. Now, so the main thing you have to be careful with when plugging in PivNerd is that you are using the gas law value that matches the units that you plugged in. Okay, and again, PV equals nRT. Therefore, I'm going to give you 3 of these 4 variables, and you should be able to solve for the 4th for any gas. All right, at normal ideal conditions. So let's try a few. All right, so here's example number 1. If I have 4 moles of a gas at a pressure of 5.60 atmospheres and a volume of 12 liters, what is the temperature? You can see I've given you 3 of the variables that affect a gas: moles, pressure, and volume. I've also given you the gas law constant, so we should be able to solve for temperature. So as you recall, PV equals nRT, and so we're going to solve for T. So let's go ahead and set that up in abstract. How do you solve for a variable? Well, you're going to get rid of NR, so you'll divide both sides by NR, and you'll be able to cancel it on this side and isolate the T. So as you can see, if you divide both sides by NR, you're going to get T equals PV over NR. Now you've got the formula that you can plug these numbers in. So we plug the numbers in. So again, P is 5.6 atmospheres, V is 12 liters, N is 4 moles. Now we've picked R, this one right here, 0.0821, because we want our units to match. And we've got liters and atmospheres and moles, and we want to solve for Kelvin, so we'll use the 0.0821. Now, when you put this in your calculator, be careful. This is a division, so either put this in parentheses, or remember you're dividing by 4 and dividing by 0.0821. So put in your calculator right now and make sure you get the same answer I do. Really, do it. Just be sure you're doing the order of operations correctly in your calculator. When you do that, you should get 205 Kelvin, okay, because the unit is Kelvin. Now, to change Kelvin into Celsius, we will be subtracting we'll be subtracting 273. So 205 minus 273 will give us negative 68 degrees Celsius. So from these conditions of 4, 5.6 atmosphere, and 12 liters, we can predict the temperature of that gas would be negative 68 degrees Celsius, or 205 Kelvin. All right, let's try another one. All right, example number 2. And again, notice I've given you the R constants. You just need to pick the right one based on the units. So if I have 7.7 moles of a gas at a pressure of 105 kilopascals and at a temperature of 56.0 Celsius, what is the volume of the container that the gas is in? So now we've got PivNerd again, PV equals nRT, and we've got to solve for V. Well, how do we do this? We're going to divide both sides by P, right? So again, PV equals nRT, and so we've got V equals nRT divided by P. Now we get to plug in. All right, so now you got to remember that these gas laws are always assuming the absolute scale. So you're going to have to change temperature into Kelvin. So before we plug in here, we're going to have to change 56 Celsius into Kelvin, which means we're going to have to add 273 to it. If we do that and plug in nRT over P, we've got our moles. Now I picked 8.314 because notice our pressure is in kilopascals, so we have to use the R unit that's in kilopascals. So 7.7 times 8.314 times 329, because 56 plus 273 gives us 329, divided by 105, and that should give us 201 liters. And again, think about this. We got 3 sig figs all over here, so that's why we round our answer to 3 sig figs. Okay. Now we got one more law to learn in this unit. It's called Dalton's law, or Dalton's law of partial pressure. In words, it says the total pressure is the sum of the pressures of the gases in a mixture. So if we have a container of a mixture of gases, then the total pressure is going to be the pressures of the gases in the mixture. Because remember, pressure is caused by collisions. So depending on how much gas is in the container, it will have a certain number of collisions. So here's the equation. So the total pressure of a mixture of gases in a container will be the what's called the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C, and however many gases we have in that contained mixture. Now, the partial pressure of gas A, so P sub A is the partial pressure of gas A, is going to equal the mole fraction, which is just the percent of the gas that is gas A times the total pressure. So in other words, if gas A is 50% of the gas in the container, it's going to be 50% of the collisions and therefore 50% of the total pressure. And again, we're going to learn how to calculate what's called this mole fraction, which is just really the percentage of the gas that is that particular gas in the container. All right, so let's look at a couple of examples. The total pressure of an oxygen-argon-helium gas mixture is 755 millimeters of mercury. Remember, that's a unit of pressure. If the partial pressure of the argon is 174 millimeters of mercury and the partial pressure of the helium is 389 millimeters of mercury, then the partial pressure of the oxygen is what? Okay, so let's employ Dalton's law. Dalton's law says that the total pressure is going to be the pressure of the three gases added up. So we know the total pressure, and we know the pressure for the argon, and we know the pressure for the helium. So we're just going to solve by subtraction for the pressure of the oxygen. So be sure to pause the video and see if you can solve for it. So here's 755. Here's the pressure of the argon. Here's the pressure of the helium. We're just going to subtract 174 from 755 and 389 from 755 to get the partial pressure of the oxygen. So 192 plus 174 plus 389 will give us the total pressure. Easy, right? Well, let's talk a little bit about this idea of partial pressure. That's example 2. So the total pressure of an ideal gas is 2 atmospheres. It is a mixture that contains 20% oxygen and 80% nitrogen. So the mole fraction, or the percentage of the gas that's oxygen, is 20%, and of nitrogen is 80%. Now think about this. This is just air. This might be something in the balloon, okay? It's just air, okay? So we want to know the partial pressure of each gas in this container. Now hint, the mole fraction of each gas is just the percentage. Okay, so let's set this one up. We know the total pressure is going to be the pressure of the oxygen plus the pressure of the nitrogen. Now, what's the pressure of the oxygen? What's the pressure of the nitrogen? Well, they're just the mole fraction, or the percent that's oxygen, times the total pressure, and the mole fraction, or the percent that's nitrogen, times the total pressure. So we're just going to plug in those numbers. And again, remember, how do you find 20% of a number? Well, you convert it to the decimal. So look at this. We've got 20% of 2, or 0.2 times 2 is 0.40 atmosphere. So that's the partial pressure of the oxygen. Move myself up here. And partial pressure of nitrogen, which is 80% of the total pressure, is 0.8 times 2, which is 1.6. And notice how the sum adds up to the total pressure. But the pressure of the oxygen is just the percent that's oxygen. And the pressure of the nitrogen is just the percent that's the nitrogen. Again, remember, pressure is collisions. So if 80% of the particles are nitrogen, then 80% of the collisions are nitrogen, and 80% of the pressure is nitrogen. Okay, so here we gave you essentially the mole fractions, but can you calculate them? That's what this next example will do. All right, whoops, let's go back. All right, so here's example 3. What is the partial pressure of carbon dioxide in a container that holds 5 moles of carbon dioxide, 3 moles of nitrogen, and 1 mole of hydrogen, and has a total pressure of 1.05 atmospheres? Now this time we're going to have to calculate the mole fraction. And it's asking for the mole fraction of carbon dioxide because it's asking for the partial pressure of carbon dioxide in the container. So let's remind ourselves what a mole fraction is. It's just a percent. It's just a part. So the mole fraction is going to be the moles of gas A. In this case, we're going to use carbon dioxide over the total moles of the gas. So we know we've got 5 moles of carbon dioxide, but we also have 3 moles of nitrogen and 1 mole of hydrogen. So we'll just add those all together to give you the moles of the gas. So how do you do the mole fraction for the carbon dioxide? So 5 is the moles of carbon dioxide, and the total moles in the container is 5 plus 3 plus 1, or 9. So 5/9 of the pressure is due to the carbon dioxide, or 5/9 of the gas is the carbon dioxide. 5/9 is the decimal 0.556. Use 3 significant figures. You can just also use the fraction itself. Now, how do we figure out the total? We're going to multiply. How do we figure out the amount that is due to carbon dioxide? Well, we know the total is 1.05, and we know that 5/9 of that is due to carbon dioxide. So you're just going to do the mole fraction, which is 5/9 or 0.556 times the total pressure. If you do that, you'll put 0.556 times 1.05, because that's the mole fraction, times the total pressure, and you'll find that the partial pressure of the CO2 is just 0.583 atmospheres. So that is your lesson on all the gas laws, and you'll get to do some practice.